Hey everyone, in this video I'll be covering the final grounded locomotion states in the locomotion state machine for Lyra, the cycle state and the pivot state. Alright, I have Lyra's main animation graph open. I'm going to navigate into the locomotion state machine. So far I've covered the idle state, start state, and stop state. Next I'm going to cover the cycle state. But before I open it up, let's look at the transitions that are connected to it. So, from start, we can enter the cycle state if the start animation is finished playing. We can enter the cycle state from start if the start direction is not equal to the current velocity direction. So if we've rapidly changed direction while starting, we're going to switch into the cycling state. If we change from crouching to standing or standing to crouching, if we begin aiming down our sights or stop aiming down our sights, or if we've been in the start state for more than 0.15 seconds and our displacement speed is less than 10. It'll also go from start to cycle if the linked layer has changed, meaning if the linked animation layer containing, the linked animation blueprint containing the animation layers has changed. For example, we switch weapons while we're starting, then we're going to switch to cycling. Finally, if the absolute value of the root yaw offset is greater than 60, we go from start to cycle. I'll go ahead and read this comment, which explains why. Transition to cycle early if the offset is too large. Example, if the camera is on the right side of the character and the user presses forward, we don't want to strafe left for a long period of time, we want to jog forward. This transition uses the sync group name to require valid markers rule setting to ensure that we wait until there are valid sync markers so we smoothly enter cycle. So here is that sync group name to require valid markers rule. If I hover over it, it'll give us an explanation. If sync group name is specified, transition will only be taken if the sync group has valid markers. Other transition rules still apply in addition to that. So, this will ensure that the animations are synced up if this transition is being used with sync markers before it transitions. That is not the case for the other three. Also make note that these are using different priority orders as well. I entered the cycle state there, but I've just exited again because I also want to cover this one other transition from cycle. We can go from cycle to stop. So we can enter the stop state from the cycle state based on two conditions. We have a has acceleration boolean, which goes into this OR, and we also have an AND, which feeds into this OR. This AND is taking in a gameplay tag is melee and a has velocity boolean. So this AND will fire off a true when we are meleeing and we have velocity, which will make this OR fire off a true, but this not is going to convert that to a false, therefore we cannot transition into the stop state if we are meleeing and we have velocity. Or if we have acceleration, we're not going to enter stop, but if we do not have acceleration, we will. Now I'll enter the cycle state here, and we have again this jog lean Ziblin space, an apply additive node, an output animation pose node, and a full body cycle state linked anim layer. Let's go ahead and move over into the base item anim layers animation blueprint. I'm going to navigate into the full body cycle state layer. And it's very similar to the start and stop layers. We have a sequence player with an update cycle anim function assigned, a sequence evaluator for hip firing, orientation warping and stride warping, which I touched on in the previous video, and an output pose. So we only have one bound function this time around. Well, we do have another if we count the hip firing, an I'm going to go ahead and just click this magnifying glass here, and that'll take me straight to the function. Don't ask me why I haven't been doing that in the previous videos. I really have no idea. It's much easier than typing out the name of the function and clicking on it over here. So the first thing we do is we set a sequence with inertial blending. And you'll notice that we're setting the sequence on update for the cycle state instead of whenever the cycle state becomes relevant. This is because we can change directions while in the cycle state without needing to exit or re-enter that state. So with starts, you're not going to switch to a different start animation once your start animation is playing, but with cycling, you're going to need to have that ability to switch between different animations, a forward, backwards, left, and right animation. So in some situations, like from forward to backwards or from left to right or vice versa, you're going to switch into the pivot state. There are going to be situations where you're just going forward to left, left to backwards, that sort of 90-degree change in direction that's not going to cause a pivot, where you're going to need to switch animations. And so that is why it is evaluating the direction and a couple of things here with booleans every update to see if the animation needs to be changed. If we are crouching, it's going to choose a crouching animation based on the local velocity direction with no offset. We have a variable here of that same struct type as all these other animation selecting functions, which is the anim struct cardinal directions. However, if we're not crouching, it checks if we're aiming down our sights. If we are, then we're going to play walking cycle animations. If that's false, we're going to play jogging cycle animations. I'll set the sequence. It'll set the play rate of the animation to match the displacement speed of the character each update within a clamp of 0.8 and 1.2. And then it sets a stride warping cycle alpha with the finterp node. So we're interpolating the current stride warping cycle alpha to either 1 or 0.5 based on whether or not we're running into a wall. We also take in the delta time as usual with an interpolation speed of 10. And that really is all there is for the cycle state. It is super simple compared to the distance matching that's needed for starts and stops. Alright, here we are inside of... So, I went ahead and started playing just so that you guys can see the cycle state. It's pretty simple. We're playing a forward animation here. Now we're going right, playing that right animation, and we're using orientation warping to blend between these different directions. I do not have my gamepad plugged into my computer currently, so I'm just using my keyboard here. Here we can see that we have 4 cycling animations that are being used, and we're using orientation warping and stride warping to match speeds correctly. Now I can aim down my sights and look down, and you can see that it's playing a walking animation instead of a jogging animation now. Next, the final state in the ground locomotion section of this locomotion state machine is the pivot state. We can enter the pivot state through a state alias. I touched on it in a previous video, but to refresh everyone here, because it is new in Unreal Engine 5, it's a way of just keeping graphs organized by essentially it can serve as a transition to pivot with a rule from any selected node in the graph. In this case, start and cycle are selected, meaning that we can transition from cycle or from start into pivot. Whoops, I did not mean to double click. If this transition condition is true. And this condition is checking whether or not the dot product of the local velocity and local acceleration is less than 0, meaning that there is quite a difference between velocity and acceleration. Because remember, Acceleration is the force being applied to the character to move it. Velocity is the result of that force being applied and friction and other things being taken into account. So if the acceleration does not match the velocity, that means the player has just changed their direction and the character has not yet adjusted to that change in direction. However, this is plugged into an AND node here, which is going to ensure that the character is not running into a wall. If the character is running into a wall, then whatever state the character is in, they're going to stay in that state and they're not going to pivot. Now, from the pivot state, we can exit the pivot state into the stop state if we do not have acceleration, meaning the player is no longer trying to move the character. We can move from pivot into start if the linked layer has changed, if the crouch state has changed or the aim down sight state has changed, or if we are moving perpendicular to our initial pivot and the last pivot time is less than or equal to 0. That last pivot time variable is a variable that allows you to very briefly at the beginning of a pivot animation to switch your pivot to a different pivot if you've changed directions. However, once a time threshold passes, Lyra has it set to 0.2 seconds, you can no longer change your pivot animation and you will just exit the pivot state to cycle. And this is moving perpendicular to initial pivot function, is just checking if you're moving perpendicular to the initial pivot. There's not much more to it. I do cover it in more detail and walk through a couple of logical examples with it in the previous video where I cover the overall animation graph. There's still looks like there's still one more transition here. And this is testing if an anim notify state is active in the source state, which is transition to locomotion, which would just be an anim notify state assigned to an animation, and if the animation is in a portion where that state becomes active, it's going to transition into locomotion. Let's see if we can't find that state in one of the animations. So I'm going to go into animations, locomotion, let's do unarmed, and I'm going to search up pivot. Let's do jog, forward, pivot. So we're pivoting from forward to backwards. And here's that state, transition to locomotion, which happens at the end of the pivot. And I will go ahead and uncheck both of these, enable root motion, and I meant to uncheck force root lock. So now we can watch the animation and see what's happening here. So once it gets to this point, it's going to transition back into the regular cycling animation. And it looks like that last section of the pivot should match the cycling animation it's transitioning to, so I was curious to see if it was going to use inertialization, but it isn't. And that's it for the transitions to and from pivot. So let's open up the state. Again, it's fairly simple. There's the regular jog leans additive. We also have some functions bound to this output animation pose. So let's look at that setup pivot state. It's a very simple function. We just take the local velocity direction and we set a pivot initial direction variable. And we'll see where and how that's used shortly. We have an update pivot state, which is slightly more complex, but still very simple. We just check if the last pivot time is greater than 0. If that is true, we subtract the delta time from last pivot time and set last pivot time. So we are constantly incrementing last pivot time down. And that's it for the bound functions in the main anim graph. Let's head back over into that base item, that item anim layers base animation blueprint, which I did close for some reason. I'm not sure why. I'm opening it up again. And now let's navigate to the full body cycle states. The full body pivot state layer. Here it is. Unlike the other start, stop, and cycle layers, it is using a state machine with multiple states. However, the state machine has no function bound to it. neither does this output pose. And then it's also just blending in that same update hip fire, raise, weapon, pose, bound function. So let's enter the state machine. And we should note there's only one max transitions per frame, and I forgot to look at and share whatever that this was set to in the previous state machines. So it may not be set to the default of 3 in the other state machines that I covered in previous videos as well. And in it we have 2 states. And now this is because when you're pivoting, you can enter another pivot, but because in the main anim graph you can only enter the pivot state from a state that's not pivot, there's no way to start over and pivot in another direction from within that pivot state unless you put a state machine inside of it with 2 more states. Each of these states are identical to the other. They transition with the same rule, which is checking whether or not the dot product between local velocity and local acceleration is less than 0. So the same condition as the main anim graph, but 2 other conditions also have to be true. We must not be moving perpendicular to the initial pivot, which means we must not be moving, like going forward to right or forward to left, that 90-degree change. And the dot product of the local acceleration 2D and the starting acceleration of the pivot must also be less than 0. And this is the same transition used here. It's an inertialized transition with a duration of 0.4. And both of these pivot states are the same, so I'm only going to cover one. The same orientation and stride warping setup is the other states. And then we have, I want to check if there's anything bound to this. Output node, nope. So we just have 2 functions bound to a sequence evaluator with a dynamic sequence and dynamic explicit time. We have a setup pivot anim function and an update pivot anim function. So let's take a look at the setup pivot anim function. We're getting the main animation blueprint's local acceleration 2D and setting that pivot starting acceleration variable that we just saw. Next, it's setting a sequence using a function named getDesiredPivotSequence. And it takes in the cardinal direction from acceleration variable from the main animation blueprint. So this node is the same setup as pretty much every other bound function that selects animations using the select nodes, cardinal directions, and booleans. It checks whether we're crouching, whether we're aiming down our sights, and chooses animations based on the direction in those booleans. And nothing new in terms of concepts here. Next, it sets the explicit time to 0 because this is the setup pivot anim node, and so it's resetting the time for the evaluator to 0. It also is resetting the pivot alpha for stride warping and the time at pivot stop. It's also setting that last pivot time to 0.2, but it's setting it inside of the main animation blueprint. That's it for the setup pivot anim state. Or function. It's relatively simple. Now this update pivot anim function is probably the most complex bound function in Lyra's animation graph, animation locomotion setup, and I'm just going to cover it bit by bit until we're all the way through. It seems daunting at first, but it is actually fairly easy to understand if you just take it one piece at a time. We first set a sequence evaluator variable just so that it's easier to access that value elsewhere in the blueprint because it is so large. It also sets as you note, this is a local variable. This explicit time variable is also a local variable. Once this is set, we move over into a sequence. The first thing we do is we check the last pivot time variable, check if it's greater than 0, and if it is, then we allow switching to a new pivot animation. So if it is greater than 0, then we set a new desired sequence variable using that same getDesiredPivotSequence function with the same input. Then we check to see if this new desired sequence is not equal to the current sequence. If it is not equal, then we set a sequence with inertial blending. We set with the new desired sequence, and then we reset the pivot starting acceleration variable. But if this is less than 0, meaning 0.2 seconds have passed since we've started pivoting, then we're not going to do anything here. Next, we're going to check whether or not acceleration opposes velocity using the dot product here, meaning that if acceleration opposes velocity, we haven't gotten to the point in the pivot where we've switched directions, we're slowing down. And we want to do two different things. When we're slowing down, we want to distance match to that predicted point. And when we're speeding up away from that point, we do not want to distance match to a predicted point anymore. Previously in Paragon, Epic switched those two stages into two separate states, a state for getting to that point and then going away from that point. Now they've built it in a way where it does not have to be that complicated, which I really appreciate because it does remove a layer of complexity in trying to get these things to work. And I'm speaking from experience because I tried to get this figured out myself, pivots and distance match pivots in my own setups in the past, and it is pretty hard. And they use some. I really can't understate how much of a fantastic resource Lyra is for anyone looking to learn how locomotion systems are built and how to build their own. So, while acceleration opposes velocity, the character is still approaching the pivot point, so we distance match to that point. So we use a distance match to target node just as we do in the stop updates function, and the input for distance to target is the result of this predict ground movement pivot location function, which is a function built into the same Locomotion library plugin that allows you to use the distance matching functions as well. So it takes in values from the character movement component, feed in the evaluator and the locomotion distance curve name, and then we set this time at pivot stop with the elapsed time of the animation, because when this switches to false, we want to use that time at pivot stop, and it'll be updated to whatever we want to use that time at pivot stop. So once we are now moving away from that pivot stop point, we set the stride warping pivot alpha based on this calculation here. So we have a stride warping blend in start offset and a time at pivot stop. So we're not stride warping until we're moving away from the pivot. So we take the elapsed time of the animation, subtract the time at pivot stop. So at this first update here on false, this is going to be the same thing. So we're going to get a 0. Then we're going to subtract stride warping blend in start offset. So this offset, which is set to a default value of 0.15. So now we're at negative 0.15. So that's going to be mapped to the range of, well, it's going to be 0. And finally, once 0.15 seconds have passed, let's say 0.16, we're going to be at 0.1, and we're going to begin to blend in the stride warping pivot offset. And the time it takes to get from 0 to 1 is determined by this in range B, which is the stride warping blend-in duration scaled, so 0.2. So after the 0.15 second offset has passed, we then take 0.2 seconds to go from 0 to 1. Then we advance time by distance matching. So we take in the displacement since last update. So we do the same distance matching function as the starts, and we advance the time based on how far we've traveled in the last frame, or for the last update. We also put in a play rate clamp, which I believe is done the same way as the starts as well. So a lot of stuff here in this function that it's big, but it's reusing concepts we've already touched on in the past. We have the clamp variable, which goes from 0.6 to 5. We break the vector, and we lerp the 0.2 to the clamp based on the stride warping pivot alpha, and then we make the vector again and plug it in. And I went over why this is done in more detail when I covered starts, so you can refer back to the starts and stops video to understand this a bit better. I'm not going to go into it in as much detail here because I already went into it in detail more detail in that video. And so that is it for the pivot state. I'll go ahead and play. So here I am back in one of the game modes for Lyra, and we can see that pivot animation play from left to right and right to left is I quickly switch from holding down the A to the D key or the D key to the A key. And again, it'll do the same thing, of course, if I switch from pressing the W key to the S key as well. However, we will not pivot if I go from the W key to the A key. We will just rotate with, we'll just blend to a different animation with orientation warping. So we have to, because of that dot product, we have to change, there has to be a change in direction that is greater than 90 degrees for a pivot to be entered. All right, everyone. So that is it for the ground locomotion states in the Lyra animation blueprint. So it was a lot, but we finally gotten through a big chunk of the blueprint. We have the jump states left, which I believe I might be able to cover in a single video, which will be the next video. If not, I'll split it up into two. And then it's on to some of the other things the main anim graph does outside of locomotion. And that'll be it for the series. So I hope you enjoyed the video. I hope you learned something from it. If you did, be sure to subscribe to the channel and give the video a like as well. It really helps me out. Thank you for watching, and I'll see you in the next video.